So section 18.1 is about electrical potential energy. There's going to be two objectives. The first, to define what this actually is, what it actually means. And second, to compute the electric potential energy for various scenarios or different parameters needed in those scenarios. So let's start by defining it. First, think of potential energy as you've thought of before with gravitational potential energy and spring potential energy. It's the energy of possible action or like stored energy. Okay? So it's the potential energy that's associated with an object due to its position relative to a source of electric force. Okay, due to its position relative to a source of electric force. So for example, if a charged particle is in the region of an electric field, it feels an electric force, and thus it has potential electric energy, or electrical potential energy. Look at the first formula real quick. A potential energy that's electric. I'm going to use PEE when I write it in the equation, just a little e. Take a look at the formula and think about that for a moment. What does Q stand for again?
Heat? No.
It's heat with thermodynamics, but what have we been doing with the charge? The charge. What does E stand for from section 17.3? What is it? The field, good. The electric field strength. And then D stands for usually? Distance. So we've got charge times the field strength times the distance. Where does that seem familiar to you? Or where does that ring a bell? Or how does that make you think of something else?
Like normal potential energy?
Yeah, exactly right. Very good. What's normal potential energy? What's the formula of potential energy? Normal. Gravitational. MGY. What's MGY? M is now Q. Instead of a mass of an object, we have a charge of an object. E is from the G. G was the gravitational field, right? Well, E is electric field. Y is the height. Well, D is distance, meters. Do you see the analogous nature of these equations? Okay? Again, just like the examples we've gone over already with, remember the pendulum and the spring mass system? The period was 2 pi radical L over G for this pendulum, and the period was 2 pi radical K over M for the spring mass. Those were analogous. They were pretty much the same formula for two different scenarios. Same thing occurs here. Now, we're going to use the latter of these equations though here at the bottom. How do you get that bottom equation? Anybody suspect how you might get that bottom equation there?
It's like the same thing as the other one.
It does look like the other one. Remember the other one was this. Yeah, very good, F. The other one was R squared. That's this down here, so don't confuse these two. We'll write it on the side. That's a side note. That's the electric force, and now we're looking at the electric energy, or the potential energy. If you take calculus in college, you'll learn how these are related with what's called the derivative. But where does the PE electric come from at the bottom there, the second version? How can I get from the first one to the second one? There's one substitution you can make.
Isn't that like KCQ R?
Square. Yes, that's exactly right, Bobby. So replace this E here with KCQ over R squared. And then this becomes well, D is distance. What is R in this problem, though? It's also distance. So watch. Cancel, cancel. Now you have KC. This is the Q from the actual source. This is the Q from the location of where the charge is. Kc is our constant. And we get this formula right here. The negative indicates, is there going to ask? Because distance and R happen to be the same thing. They're different variables, but isn't R the distance between the particles? Remember what was R defined as in these problems? The distance between the proton and the electron, right? Well, D happens to also be the distance between the source and the object. The source might be the proton or a charged positive region, and the object might be an electron. So they happen to be different variables. They look different, but they mean the same thing. So I can reduce them. It's like having an R on the top. The negative comes from the fact that it's a reaction, but don't worry too much about the negative for this case, okay? In the original formula, I mean. Okay, so we're going to be looking here at this formula. All right, let's take a look at an example. Just two examples today. That's it. We're going to look at two examples. The first one is pretty straightforward. The second one, we want to take a look at a possible experiment that could be set up. But let's look at the first one first. Mike, leave that alone, please. The electrical potential energy associated with 2-point charges of 5 microcoulombs and 4 microcoulombs is -6 times 10 to the negative third joules. Why do you think that that energy is considered to be negative? Because the objects are doing what?
Repelling.
Attracting. Attracting, be careful. When they're repelling, when they're repelling, it would be positive. It's the worst. Who was it? It was the other day I was in class. Did anybody ever bite their cuticles?
Yeah.
Anybody do that? Or bite their nail? And you ever you bite your cuticle and obviously your cuticle's on your lip now or
Yeah.
And I was talking as I did this. I was just biting my hand, and I spit a cuticle, and the piece of my skin, and it landed on the side of Garrett's face. And I was like, "Oh my God, Garrett, I'm so sorry." And it was 2 feet away, but just when you talk, you naturally. I mean, everybody spits when they talk. Look at your iPad screen. You probably always,
Yeah.
It was just so funny. Oh my gosh, because I'm in the middle of teaching, and I'm getting into it, I'm talking, and then all of a sudden I just see it launch, and I see hit him, and he's like, and I'm like, "Sorry." Yeah, but I did see that. It's gross, right? Yeah, in the middle of forensic science. We were doing a lab. But still, it was still in the middle class. All right, so we know the charges on the particles. We know the energy stored, or the energy between them that's created due to their locations or their positions. And we want to determine what is the distance between them. What are their relative positions? So if this particle is here, how far away is it? Well, if this particle is here, now how far away is it? And they're going to stay that distance apart. Okay? So let's go ahead and figure this out. So let's take a look at our formula that we just wrote down. We have potential energy induced by electricity equals Kc Q1 Q2 over R. Remember, it's not over R squared here. So please don't fall into that trap of writing R squared. If it's R squared in this formula, you're looking at the electric force. Here you're looking at the electric potential energy. So you could say that the potential energy and the force differ by a factor of R, right? And that's where that derivative comes into play when you take calc. All right, let's take a look. What are we solving for, Mike? What are we looking for? R. So Thomas, tell me, what should I do to get R by itself?
Just switch potential and R.
Very good. You guys are pros at solving equations now, right? After this class? Just simple one variable equation like this. By one variable, I mean one variable of interest. So we have R as a generic solution. We plug in at this point. What does a microcoulomb mean again? Yeah, times 10 to the negative 6.
Why did it go from being PEE to PES?
It shouldn't. That's a typo. Thank you, Camila. PEE, not PES. Very good. All right, so one of the charges is negative 5 microcoulombs, the other one's 4. So we've got R equals Kc. Yeah, very good, Ev. Then negative 4 times 10 to the negative 6. And 5 times 10 to the negative 6. Is it backwards? All right. I just guessed. Sorry. Thanks. I realized that as you asked that question, it must have been.
It doesn't matter, right?
In the end, it doesn't matter now. But we should write it in the correct order. And we're trying to put this over the electrical potential energy, which is negative 6 times 10 to the negative third joules. A very small amount of energy. Why is it a very small amount of energy?
Is it already reached it?
No, not in that sense.
Wait, I'm confused. It's not a lot.
It's not a lot. The energy is not a lot.
Not a lot. Or the distance, they're close.
Well, we don't know. We're trying to find the distance. That's a good point, though, and that has to do with it.
Okay.
But why is the energy maybe small? If the energy is small, or a small amount, what could you probably say about the distance between them? Yeah, generally speaking, but we don't know what it is yet. Okay? So there's a good chance there's going to be a good gap between these two particles for such a small quantity of energy. What do you get for R? 30 what? Base units always. Whenever you solve for something, if everything is in base units, the answer is in base units. Always. Yeah, 30 meters apart. Okay, so we're talking about from the end of this classroom wall all the way to that other side of that classroom wall. It's a big gap between the two charged particles. Okay, so there's such a small amount of potential energy that exists between them.
Bless you.
Let's take a look at the next one. The next one's a little more realistic, okay? Can I get someone to read this for us nice and loud? Thanks, Catherine.
A certain amount of electrical potential energy is needed in an experiment to keep two charged particles separate from one another, but the locations of the particles are placed in space. If the distance between them is 85 centimeters, one has a charge of 7 nanocoulombs, and the required energy is 2.6 times 10 to negative 7 joules. Then determine the charge needed on the second particle.
So think about this in the case of, well, if you want something not to move, but they're charged, so they're going to want to repel or attract one another, and you need them to stay fixed in space because you're performing an experiment. Well, they have to have a certain charge so that they remain fixed in space. Well, this is the example of that. So we have to figure out the second charge, or the charge that needs to be induced on the second object in order for these two objects to be separated by 85 centimeters. Okay, so let's go ahead and figure out what that is. So what do we know in this problem?
PE.
Q1.
R.
Wait, is the PE the required energy?
Is PE the required energy?
Yeah.
It is.
R equals
It's the only energy in the formula, right?
Okay, yeah.
R is?
0.85.
Okay, converting to meters, very good. Energy, have you said that was?
2.6 times 10
And then Bobby, the Q one? I thought you said it, sorry.
Is it 7 times 10 to the 6th?
What's a nanocoulomb? Micro is -6, remember?
Yeah, so is it
The
6?
negative,
Oh.
I thought I heard it twice. I heard it in the back also. -9, okay? So we're looking at like on the nano scale as far as energy is concerned. And we're looking for Q2, the other charge necessary for this experiment to actually work or hold true. So let's solve for Q2, which is a little bit more complicated, but not much. What do we got? How do I solve this one? Scott, you want to help me out for Q2 here? Okay, so we want to get Q2, so we're going to definitely need to get rid of these by dividing, but before we divide these, how do we get rid of the R? Yeah, because R is currently dividing, right? So let's multiply by R to start. And now, because we remember that Q2 needs to stay up top, we'll divide by this coefficient, right? Isn't this really a coefficient in front of Q2? It's like a number, a quantity. If it was 5x and you wanted x, you would divide by 5. So divide by KCQ1. You can divide by more than one thing at once. It's just a product, right? So this is our answer for Q2. R times PEE over KCQ1. What do you need to remember to do on your calculator? Please.
Put the denominator in parentheses.
Put the denominator in a major set of parentheses. By major, I mean make sure there's a set of parentheses that is specifically designated just for the denominator, around the whole denominator. Is that clear? Crystal. Awesome. Well, the question is crystal really too clear? I like that saying, but doesn't crystal actually refract light pretty? Right? Where's crystal clear come from? It's crystal. I mean, I get it. You can see through it, but light's got to be bent.
Maybe crystal clear.
Stretching it way too far.
Maybe crystal clear used to mean like, oh, I kind of get it, but I'm gonna bend your words.
Yeah, because I think it was around before liquid crystal display, but I get you.
I'm gonna bend your words.
What do we get for a number here? Should all be checking this, I hope.
Is it 3?
8.5 times 10 to the 9. That's 0.501.
Units of? So it's 10 to the negative 9, so what should I really write for my units to make it easier? What should I write?
Nanocoulomb.
Yeah, it's just 3.5 nanocoulombs. Again, 10 to the negative 9, we said a minute ago was nano, so why not write it as nano? Just makes it easier.
If you leave it like that, we just take off.
Unless if I specifically say express your answer in nanocoulombs or in, some unit, obviously I want to see that you can do that. Okay? Any questions on this? Yeah. Because times 10 to the negative 9 really means nano, right? Remember earlier when we had nanocoulombs, we wrote it? It was 7 nanocoulombs given. We wrote it this way. So if your answer comes up this way, just write it this way.
-6 is micro.
Okay? Homework as always is 2 problems here.